In this first workshop, we will implement temperature-dependent elastic behavior using UMAT subroutine writing. First, their equations are presented. As you can see, the stress equation, contrary to what was stated in the elementary training packages, is temperature-dependent despite the similarity only in mechanical properties such as lambda and mu that are temperature dependent. Note that this time the elastic strain for each component is equal to the total strain minus the strain due to temperature changes. Therefore, we see temperature-dependent term in stress and strain equations compared to previous basic stress-strain relations. When we want to obtain the stress by subroutine UMAT in each increment, we have to add the stress in the previous increment with the stress changes in the new increment. Contrary to the temperature-independent elastic behavior of materials, stress changes will be different here. So, writing delta equation for stress, the first part of the relationship is exactly the same as non-temperature dependent elastic equation of materials, and the second part shows changes in temperature-dependent mechanical properties. In addition, unlike the first part, there are no strain changes in the second part, but the strain itself is seen, and the changes are only for mechanical properties. We have above mentioned formulas for mu and lambda. To write a temperature-dependent elastic model, suppose that the elastic strain at temperature T1 is equal to E1, and at temperature T2 is equal to E2, and the behavior between them is linear. Thus, by calculating the slope of the line, you can have other parameters such as strain or elastic modulus. By having the slope of the line and a point like it, T1 and E1. The relationship between the mechanical properties of the material in terms of temperature can be obtained. For example, for the elastic modulus, the following relation can be written. If we consider its coefficients of F0 and F1 respectively, it will help us in subroutine writing. We simulate our cube model with L side dimension. The required coefficients and values are presented here. Note that the force displacement is in the z direction equals to -4. You can also see the intended coordinate system here. Here, the behavior of the material at two temperatures of 273 and 700 K is considered, which Young's modulus is 200 and 150 gigapascal respectively. In the following, we discuss how to write subroutine according to the relations and then implement it in the Abaqus software. Here we start writing subroutine. The beginning of the code is default terms to use UMAT subroutine, which should be copied here. A bunch of variables used in subroutine are introduced here. For example, elas is an elastic strain representation and others are visible. Note that the dimensions of each of the parameters used in the subroutine must also be stated, especially if it isn't a scalar. It is a vector or matrix. Also, if we want to use a series of parameters, for example, to use 0 instead of 0, we must first define these parameters here. In order to have proper accuracy in calculations, we define each scalar variables as real star 8. Each of these cases is defined below. Note that subroutine UMAT, like VUMAT, receives software inputs called props. We have defined 8 props. Props 1 indicates the elastic modulus at temperature T0. Props 2 is the Poisson's coefficient at temperature T0. Props 3 is the initial temperature, which is the same as the initial temperature we define in predefined field. Props 4 is the elastic modulus at temperature T1. Props 5 is a Poisson's ratio at temperature T1. Prop 6 is a temperature of T1. Prop 7 is the coefficient of expansion, and Prop 8 is the initial temperature. T0 and initial temperature are not same. Note that T0 and T1 are the temperatures that mechanical specifications is given on them. But in the initial temperature is the temperature that may be included in the simulation as the initial temperature. Then, as you know, we have to have an equation that gives us the Young's modulus at the beginning and end of the increment. First, according to the relation that was presented, we define the coefficient of F0 and F1, so we calculate them. In this part of code, the previous equations of F0 and F1 are written. The F1 coefficient is equal to this relation. If FAC1 is less than 1, it means that the temperature is less than T0. FAC1 equal to 0. And if the temperature is more than T1, the chart is in this section. This indicates that the calculations are based on the endpoint. So we specify FAC1 and FAC0 is equal to 1 minus FAC1, which is expressed before. Now the Poisson's ratio and the Young's modulus coefficients can now be calculated. The coefficient F0 is multiplied by props 1 plus FAC1 in props 4 is our equation. After calculating E and NU, the bulk modulus is also calculated, and then G2 and G0, and so on, lambda at the end. Then, at the end of the increment, the same calculations must be done for the mechanical properties. Because based on the equations, we need to use changes of the mechanical properties here. Therefore, calculations must be done at the beginning and end of the increment. At the beginning, we have the initial temperature, and at the end, the initial temperature should be added with temperature changes. And this sum is placed in all relations instead of the temp. It is necessary to calculate the stress as well. So, if we use two loops, in which the stress is the sum of the stresses in the previous increment and ddSTDE, or Jacobian multiplied by dstron dtemp. In fact, first expression is multiplication of a strain difference vector by Jacobian matrix containing lambda and mu. Second expression is multiplication of difference of Jacobian matrix including lambda and mu difference by a strain vector itself. This is a small part of the UMAT and VUMAT subroutine for Abaqus training package. There is a lot more valuable information in other parts of this package that you can get on our website. We suggest you do your project by saving your time and getting basic training so that you don't get tired of Abaqus errors. If we want to calculate thermal strain, it is actually equal to the current value plus d temp to get thermal strain in each increment. Then the elastic strain is calculated as follows. The total strain of the increment plus to its changes minus the thermal strain at the end of the increment. Then we store the elastic strain and thermal strain as state variables to use in the next increment or as the output of the results in the simulation. In fact, its main use is as the output of the results. In this section, we will implement UMAT subroutine for materials with temperature-dependent elasticity. We have created two models for a single element and multiple elements using subroutine and Abaqus property library. And in the end, their results will be compared. As stated in the description of subroutine, it is necessary to give the properties of the material in terms of temperature in the property module. Before that, it is necessary to draw the desired geometry, which is a cube with dimensions of 100 to 100 to 100, and we consider it solid and deformable. As you can see, we have drawn its depth 100 and the cross-sectional dimensions 100 to 100. In the property module, we considered two features for the drawn model. One of them set from mechanical menu and elasticity tab. Given that we consider the specifications in terms of temperature, so it is 200 and 150 for temperatures of 273 and 700 K respectively. Then activate Use Temperature Dependent Data, fill in the specifications according to the table and the question information. Also from Mechanical tab and Expansion option, consider Thermal Expansion Coefficient. After section creation and assigning that to cube, go to Assembly module. In Assembly module, insert the part. Then go to the Step module. The step is made of a static general type, and other settings will be unchanged. Note that for the Abaqus model, you can use the Filled Output mode and the Pre-Select option. Also, because we want to check the temperature, it is necessary to set NT and Temp in the Thermal tab. We only have one part, so we don't go to the Interaction module. In the Load module, the boundary conditions and force displacement and temperature changes should be applied to it. In Edit Predefined field, you can consider temperature type equal to 500 in initial step. In Step 1 Modified, we set magnitude to 700 K. To create predefined field, you can do as follows. Note that the displacement value needs to be given to the model. One side of the model should be fixed, as you can see. For the other side should be entered 4 mm displacement in the opposite direction. Then we have a single element in the mesh module. So we consider its size to be 100 and set it to 3D, standard library and linear. Then we go to the job module and we can perform the analysis and see the results. For the subroutine model, all conditions are the same except that in the property module in Edit Material section. Set number of state variables to 12, since in the final part of the subroutine, K1 is from 1 to n10s and n10s number is obtained 12. As mentioned in presentation, elasticity matrix for a single element has 6 components and we have 6 elastic strains and also 6 thermal strain. So n10s is equal 12, thus state V's should be 12 too. In the user material section, the inputs are entered here. According to the definitions that we have given in subroutine, and we have fully explained it. To access any of these behaviors, go to General tab and select Deep War or User Material. After that, other settings must be made in the Step module and in Field of Output Manager section. Since we want to have state variable, then we have to activate STV in State Field User Time part. The changes have been made and we can now view and compare the results in Job 1 and Job 2. You see the results of Job 1, which is the same as the subroutine model. Job 2 is actually our Abaqus model. From the Viewport section, we can view the results simultaneously. For example, for the Abaqus model and the subroutine model, we can compare the mice's stress simultaneously and see similar results. And the temperature we used to specify are now exactly the same. Each of the parameters we stored in STVs, such as the elastic strains for subroutine at STV1 to STV6, can be seen. And after that, 7 to 12 other cases can be seen. So, as you can see, with respect to the stress contour and temperature contour, it shows the same value for both analyses. The analysis is done quite correctly. We repeat this for a large number of elements. Here we go to the Mesh module and set it to Abaqus High model with a large number of elements, and this is also done for the subroutine. You can see the results in Job 5 and Job 6. If we want to see the elements as well, we have to activate option Exterior Edges from here. You see, one is related to Abaqus and the other is related to subroutine. We will have exactly the same results for both analyses, and other things can be observed and compared, such as a strain. Sometimes small steps can revolutionize previous big innovations and can be a prelude to big changes in the future. Sometimes previous big innovations need to be easier in using. Sometimes big tools do not work and each problem must be solved in its own way. This is where we come in with our solutions. Digital simulation allows us to conduct comprehensive tests in the virtual world at low cost and high efficiency. But digital simulation for today's world issues requires programming code that can solve any problems with any boundary conditions, with any materials, and with any interaction constraints. We are here so that you can professionally write and use user code for your finite element software to solve and simulate more advanced problems together. We have come to enhance finite element software with user-generated codes and subroutines. We see the future of simulation in your hands, and simulation software will be written and built with users in the future, and we will build smarter lives together. CAE Assistant is your assistant in your CAE future challenges.